One of the first observations of discrete energy levels was first detected through the spectroscopic experiments performed by Joseph von Fraunhofer, where he used diffraction grating methods to observe the light spectrum of stars in the solar system. What he found from this experiment was that parts of the visible spectrum were missing. These parts are called the absorption lines. The reason for these missing wavelength gaps of light is due to the gases in the atmosphere of the Earth absorbing light of a certain energy, and the atoms in the gas are only excited with light of a specific energy. Therefore, as you can see in the picture below, that there are dark bands in the spectrum, representing the absorption lines. In addition, other observations of discrete energy levels were seen later on, and most notably in the photoelectric effect. In the photoelectric effect, it was observed that when light, which is comprised of photons, was exposed to a surface of a metal, electrons could be ejected from the surface. However, it could not just be any light, but rather light of a certain energy threshold. If the light was below this threshold energy value, then no electrons would be ejected from the surface of the metal. However, if the light was above this threshold value, then electrons would be ejected from the surface. What this tells us is that these electrons are bound to the nucleus of the atom in the metal by a certain discrete energy, and thus can only be ejected when the photons have a greater energy value than that of the energy bounding the electron in the nucleus.
In quantum mechanics, we've learned that light is absorbed by matter in discrete quantized energy packets called photons. And even though we classically think of energy being a continuous spectrum, this gives rise to the fact that energy is emitted by matter in discrete wavelengths rather than continuous. The discrete nature of the energy emitted by matter comes from the fact that electrons are spatially confined in the nucleus. Now, we can understand spatial confinement with three quantum numbers, and the principal quantum number basically determines the energetic ordering of the system. L is the angular quantum number, and this determines the shape of the orbital the electrons in. And finally, the M, magnetic quantum number, does not factor into how we determine the energy level of the system, but it does give rise to degenerate states in the system. Now, when we were doing quantum mechanics in 3 dimensions, we used all these quantum numbers when determining our wave function, psi sub NLM. And this basically tells us the spatial confinement of a particle. Now, from this, we determine energy levels are proportional to M and L, and that's equal to h bar squared over 2ma squared times the n root of the L Bessel function. So from here, we can tell that energy is only dependent on n and L. So we know from class that n can take values 1, 2, 3, basically any integer value, and L can take values 0, 1, 2, 3, all the way to n minus 1, and m can take values of minus L to positive L. From this, we can determine the lowest energy state. So we got an n equals 1, L equals 0, and m equals 0 state would be the lowest state, which is psi 1, 0, 0. The second energy state would be your psi 2, 0, 0, psi 2, 1, 0, and so on. So clearly, energy cannot take any values that come from n or L being anything besides integers. That's why they're discrete. We can understand why the energy takes ordering like this from the shapes of the orbitals. So we know that an L equals 0 orbital has no angular momentum. A three-dimensional shape that has no angular momentum is a sphere. So we know that our L equals 0s are spherical shells. L equals 1, we know that it takes a shape something like this. Now this is the cross-section of the orbital. So to get a full picture of the orbital, you would spin this around the z-axis. However, because there are 3 axes, this shape can actually lie on any of the axes. So for the L equals 0 state, there are actually 3 shapes that the orbitals can come in with the same energy, giving rise to degeneracy.
At the hydrogen atom, we know that the hydrogen atom is simply a proton and an electron. And the electron is bounded in a potential well, which is this. And the potential well looks like this. Since the electron is in a bounded state, the electron can only exist in discrete energy levels, which is with the lowest being negative 13.6 electron volts at the ground state. And as you go higher, let's say the second state, you get negative 13.6 over 4 electron volts. And as you go higher, the energy is equal to negative 13.6 over n squared electron volts. Stop it. Now, when an electron is in an excited state, albeit at a higher energy level, it will naturally go down to the lower energy levels and eventually reaching the ground state. And when that happens, when the electron, let's say at your n equals 4 energy level, if it drops down to the n equals 1 energy level, they will emit a photon proportional to the difference in energy, or the energy proportional to the difference in energy of both states. Now, the photons released from n greater than 1, from any of these energy levels, going down to the ground state, is called the Lyman series. And these emit infrared radiation. There's also more series. Let's say when they go from excited state to a n equals 2 state, you're going to get a Balmer series. It's in the visible spectrum, so you're going to see red light and blue light and violet light, and that is your Balmer series. And then there's one more. There's the Paschen series. When you go from any excited state down to the n equals 3 state, and it's all UV. So let's say from here or from here, and this is your ultraviolet. Because the electron can only exist in discrete energy levels, when the electron drops from a higher energy level to a lower energy level, it's only going to transmit a discrete amount of energy in a photon, and the photons would have transmitted by the electron going down energy levels would also be discrete in characteristic. And this phenomenon has a lot of interesting applications in consequence to the discreteness of the energy levels.
This is Jacob. In order to demonstrate the discrete energy levels of a harmonic oscillator, Jacob represents a particle bound by the potential of a harmonic oscillator. At the ground state, he has 1/2 h bar omega energy, as represented by the sign next to him. Now, watch what happens when we add a photon of energy, h bar omega, to the system. As you can see, Jacob absorbs the photon and is excited to a whole new energy state, 3/2 h bar omega, boosting the total energy of the system by h bar omega. Sometime later, Jacob, the particle, has absorbed enough energy to be at the state 7/2 h bar omega. Now let's watch what happens as he relaxes back down to the ground state. As you can see, he emits a photon of energy proportional to the energy lost, which is 3 h bar omega.
The discovery of the existence of discrete energy levels has led to many applications. Spectroscopy is one such application, and it allows us to determine the constituent elements of matter. All elements have a spectrum which is determined by the energy levels of the atoms which make up the element. The energy levels of atoms are determined by the potential landscape created by the interaction between the electrons and the protons. So each atom has a distinct spectrum. This means that if we know the spectrum of matter, we can know the elements that make up that matter. This image shows the absorption spectrum of a diamond, which can give a gem cutter insight as to the purity of the diamond. Lasers also take advantage of the fact that energy levels are discrete. Lasers involve the excitation of electrons to a higher energy level. If you remember from earlier, when the electrons relax back to the lower energy level, they emit a photon characteristic of the difference in energy of the levels. Again, because each atom has a different energy levels, the color of light that a laser emits can be determined by choosing the element to be excited. Another application, similar to lasers in that it involves the excitation of some element, are neon signs. I'm sure you've seen the glowing signs that many stores have near their entrances. Well, these signs consist of tubes filled with a gas, which is then subject to a current. This current gives energy to the electrons and causes them to become excited. While all of these signs are called neon signs, neon only produces orange light. But other elements, such as hydrogen, helium, and mercury, can be used to produce other colors.